Okie dokie, we're live. I apologize sincerely for the change in venue. The reason being that they are, the building is under construction and apparently A407 is not usable. Well, almost the third and the fourth floor on this level is not usable. And they let me know on Wednesday afternoon that this is going to happen. So I know it's a mess. Then they gave me another building and I thought, oh, cool. Okay, another building. Then I went to have a look. It's in the forestry building. So there's no way that you can walk within 10 minutes from math there and go back to main campus. So for the moment, I know not all of you attend. So I thought we'll fit into this lecture hall, which is actually the honors committee room. So I know it's a mess, and I'm trying to find something on central campus so that I can take my little laptop and walk over, right? But for the moment, until I sort it out, just check your emails to see where the lecture will be. Okay, great. And then we have the other inconvenience that I have this document camera that's turned this way. Right, okay. Please take a seat. I haven't said anything other than apologizing for the changing venue, so you haven't missed anything. And you're the lucky ones because you still got seats. I made an educated guess that about 20 of my people will attend out of the 48, so cool. Right, okay. Where are we? Knuth Morris Pratt is by far the most difficult algorithm to get your head around of all the algorithms we've done so far. Right. So I need to stress page 760 is where I am at the moment, brute force. Right, so page 760, brute force. Can I please ask you a favor? Can you just move to the window side, all of you, so that if somebody comes in late, that they can just sit at the edge of the rows? Sorry. Thank you so much. Okay. I do apologize for the increased invasion of private space. If you're freaking out in 5 minutes' time, then move over again. Okay. Right. I have a huge private space. Anyway, okay. Right, so we have enough open space for anybody who's late. Right. So, Knuth Morris Pratt. We are looking at substring searches, right? And we had a look at brute force because the idea is so easy. How to do a substring search with brute force. You have a text, which is just a very, very, very long row of characters, and you have a pattern. And you are searching for that short little pattern, where short is relative, for that short pattern within the longer text piece of text. So you are looking for all possible occurrences, yes? So you do it character-wise. You start at the first character of the text, the long thing, and you start at the first character of the pattern, and then you compare to see if they are the same. Only two things can happen. Either they match, or you have a mismatch, right? So this is a match, this is a match. Here we get a mismatch. So I keep track of where I am in the text with an index I. I keep track of where I am in the pattern with an index J. The moment I have a mismatch, I know only one thing. I know that from the place where I started in the text, the pattern did not match. But I could have been just one off, yes, one out. So what I have to do is I have to start matching the pattern from the second place in the text, because it might be a match there. Right? So what am I doing in brute force? I am backtracking my text index. I'm backtracking I. Yes? Which means that my complexity, if the text is size n and the pattern is size m, my complexity is roughly m times n. Yes? So for every possible position where the pattern can occur, I have to put the pattern to the text. To increase, so when does that work well? When you have random texts where you very quickly get a mismatch. Okay. Why? Because you don't want to check for a very long time and then you get the mismatch. The moment you get a mismatch, you can backtrack to the next try. Okay? So if you don't have long matching prefixes, you can do this whole thing quicker. Right. Now, that's fine. In practice, on average, brute force works good. But if I have long matching prefixes, it might not be the case. Okay, if you're sort of very on top of each other, you can move over again. Sorry about that. However, there are applications where you will necessarily not have a random distribution of text characters. For example, if you're looking at binary, your alphabet is very small. It's only 0 and 1. So you will keep on checking the whole time. And the same happens with genome sequences, where you have an alphabet of size 4, ACTG. Right? So we do want to improve the time complexity of our algorithm, if possible at all. Now, the reason why the algorithm in brute force is slow, because the text index I has to keep on backtracking. So if we can work on that backtracking, then we might be able to make it quicker. And that is exactly what Knuth-Morris-Pratt does. Knuth-Morris-Pratt says, I have an index I going through the text. I will never backtrack I. I will only increase. Yes? And Knuth-Morris-Pratt does this by pre-processing the pattern. Because if you think about this, if I match until I get a mismatch, what do I know? I know exactly what my pattern looks like because that's a known, yes? But I don't know what the text looks like. But if I had matches, I also know what the text looks like because I had matches. And I know what my pattern looks like. So what Knuth-Morris-Pratt does is it says, I know what I have seen up to now. So can I not use that? So I can use that to not backtrack the text because I know what is in the text. The moment I matched and I got a mismatch, I know what was in the text. So how does Knuth-Morris-Pratt do this? Knuth-Morris-Pratt says, we are going to construct a DFA, and on Thursday morning we had a long talk about what is a DFA, how DFAs work, and so on. And Knuth Morris Pratt says, I can draw a picture of the pattern and the behavior of the pattern. So I make a state 0. If I get the character of the pattern, and that's a match, I go to a next state. If I get another match, I go to the next state, and so on. So basically, I make a linear sequence of states which match the pattern. So from 0, my pattern is AB, AB, AC. So I match my pattern A, B, A, B, A, C. Right? So if I have a match, I'm cool. But what if I get a mismatch? That's the whole point. If I get a mismatch, I must go back and try matching again. And because I fully know what the pattern looks like, I can use that to not backtrack that far. Yes. So I will always keep eye on just increasing, but this thing then tells me how far back I must backtrack just in my pattern. So I will just backtrack in my pattern. I stays fixed, right? Okay. And how does this work? We went through this on Thursday. Just to recap, because if you don't remember this, the rest of the algorithm doesn't make sense. Intuitively, if I am starting to match characters, so I'm at position 0 of my pattern, if I get the desired match, I can move on. I'm now busy with the next character, right? If I don't get the desired match, yes, the first character of my pattern is A. The first character of my pattern is an A. If I'm at the beginning of my pattern and my text has a B or a C, then surely I must stay exactly where I am because I'm not matching. I'm waiting for an A to appear, right? So A is the only thing that will advance me, okay? And now you have to understand how, so this makes sense, right? If you don't match the characters, stay where you are. Or, meneer Thesen word wakker, or you might also backtrack. Now, how does the backtracking work? If I've just recognized the character, look at A. Suppose I was here, I saw an A, it was a match. Now I get another A, yes, in the text. So therefore, what I want, what this state represents is the fact that I have seen the first A. So if I get another A, I can just stay here because I've just read an A. However, if I get a C, where am I? I have seen an A, now I get a C. That throws me off my pattern, so I have to start from the beginning again. Or another example, if I have read an A, then a B, then an A. Yes, in my pattern, I've read an A, B, A. And I get another A, which is not what I want. I want A, B, but now I'm getting A, B, A, and another A. Where must I go? To the place which says I've just seen the first possible A that I can use. Yes, because I had an A. So A doesn't do anything for me, I'm staying here. So you have to backtrack there. Yes, does that make sense intuitively? You have to get your head around it. Can I continue? That's basically just revision of Thursday's lecture. please, on page 765, there's a huge example. And I suggest you work through this, yes, just to convince yourself that, yeah, I think it works. So if I set up a DFA for the pattern, so I pre-process the pattern. Already in your project 2, you got this whole idea about pre-processing, and some of you forgot to pre-process for a binary search tree, and then you got horrendous time complexities there. Pre-processing the pattern, and remember that the pattern is typically shorter than the text. So pre-processing the pattern should be fairly cheap. Once I have this DFA, which represents the characteristics of the pattern, I can use the DFA to know where I should backtrack to every time I get a mismatch. So let's just have a short, quick look at this. This is my index I, so this is where I am in the text. Right? Then I'm reading the text. I have my pattern over here. Yes. So I have a mismatch. My DFA said, if I get a B in state 0, I stay there, right? So I stay there. I get a C in state 0, I stay there, right? I get a B, and so on and so forth. So you'll see that my J, which is where I am in the pattern and which I get from the DFA, stays 0. I stay there in the beginning until I get an A. The moment I get an A, I can move on to state 1. Then I get another A, so I'll stay in state 1. And then I get a B, and I'll move on to state 2, and so forth. Yes? So basically, this is what Knuth-Morris-Pratt does. We pre-process the pattern to get a DFA. The searching takes place by simulating, what they call simulating the DFA. Running through the text with that DFA. And what the simulation of the DFA tells me how far J backtracks. I never backtracks. Yes? So for example, here you'll see that I had an ABA in my pattern. ABA in my text, and then I hit a C, which I didn't want, I wanted a B, which means I have to start right at the beginning of my pattern again, and J jumps back to 0. So the whole Knuth-Morris-Pratt algorithm says, how should I update J? And the answer is in the DFA. So you have to get your head around that. Okay, go through the example, make sure that it makes sense. It's all about how do we update the indices. How do I update I? I never do. It just increases. How do I update J? Well, I know what I've seen so far, so I just have to know how far to backtrack with J. Okay. So doing the search is very easy as far as code is concerned. As far as code is concerned, blah, blah, blah. This is just setting up everything. My search says, I go through the text and the pattern, and I look at the character I have at index I. Yes, text.char at index I. I look in my DFA where I am with J, and I put that into J. So it's a single for loop that does this. I think this is tremendously impressive. And when I'm right through it, I stop. So the only difficult thing now is how do I set up that DFA? Because I had all these vague intuitions and sort of, yeah, you can see you have to backtrack there and so on. But clearly you have to write a program to set up the DFA. And that is not easy. The code, again, is very compact, right? So the code doesn't really, it takes some time to get your head around that code. Okay. So let's look first what we do, what we have for the DFA, right? The easy part that we have is if I have a match, I continue to the next state. That's the easy part, right? So somewhere along the line, the DFA just goes to the next state. So that's the easy part if I have a match. If I have a mismatch, I must know where I have to calculate where to go to, which is not clear at all. Now, the way we represent that picture in a data structure is a matrix. Okay, so let's just get the matrix straight, otherwise the code doesn't make sense. I have a matrix DFA, yes, with a number of rows that is the size of the alphabet. Right? And for each row, and a number of columns, which is the number of states that the DFA can be in. In this case, the length of the text pattern. Sorry, the length of the pattern. Right? So what this thing does is the following. If I am in state 0 and I see an A, how does this relate back to this data structure? I am in state 0, I see state A. What must I do? To which state must I go to? In this case, it's 1. Yes. If I am in state 0 and I see a B or a C, I must stay in state 0. Yes, so the entry in DFA, I don't want to use I, CJ tells me for the Cth alphabet character, and I am in state J. If I'm in state J and I see this alphabet character, to which state must I go to? Right? And I read this straight from the matrix. Does that make sense? Okay. So this is just a diagram representing exactly that. Okay. So what we want to do, which is a tricky code, is we want to write code that will build this DFA. Okay? So what we have to look at is the matches. Yes, Mr. Wolf.
That matrix, it would go all the way up until how many other different types of characters you were searching, right?
Yes. So
if we were using
so
Unicode, we have 65,000 rows.
Yes. Basically.
yes, absolutely.
Is that pre-processing worth it then? Because then the space efficiency with Unicode would be
In general, remember where we use Knuth-Morris-Pratt. We use Knuth-Morris-Pratt where we have a small alphabet. Remember, that's what I said in the beginning. In Unicode, it might be worth your while. Well, in Unicode, it might be, let me get this straight. You are looking at a time-space trade-off, always. If you want to increase the time, you have to increase this. If you want to decrease the time, you have to increase the space. If you want to save space, you will necessarily increase the time. That's how algorithms always work. You have a time-space trade-off. So what you would have to do is say, well, how important is space to me and how important is speed? Yes. Also, with Unicode, you probably will be able to assume that your text has a random pattern. You would very seldom be using the Unicode alphabet and then just have strings of A's and B's. Yes? Okay. The question then to answer whether it's worth it to have this huge DFA, the answer is yes, if it's applicable. So my text surely normally is random, not with long prefixes. It might be worth it if my speed is that important. So it depends on the application, always. Okay, right.
Is there another algorithm that comes up where we analyze the substrings of pattern like we do now?
Another algorithm that comes up.
Yeah, and in this section, do you learn another algorithm
Yes.
like this one
Yes.
that also analyzes
Yes.
repetition?
We actually will do 3 algorithms. This one is Knuth-Morris-Pratt, the next one is Boyer-Moore, and then after that, they're very similar. And then after that, we do the so-called Rabin-Karp fingerprinting, which is totally different. So we'll do 3 algorithms for substring searches, of which 2 are very similar, and the fingerprinting is totally different. Okay, great. So the problem now is, how do I set up the DFA? Because I can look at it and know where to backtrack. But clearly the algorithm, I want to set up an algorithm that can pre-process my pattern. The code is ingenious. The code is simply this. One, 2, 3, 4, 5, 6 lines, which does this. And if you look at it, it does not make sense whatsoever in any way, because the DFA uses its current state to construct the next state. So it's, in a certain sense, a self-constructing process. So let's go through it and see what happens. Firstly, if you break it down, it makes more sense. So let's have a look. In the beginning, becoming biblical. In the beginning, what you want to do is you want to initialize, right? So what I will do is I can fill this in by hand as an initialization, because I know what my pattern is and I know what my text is, right? So if I get a match, I fill in a 1, right? Because I am at state 0. J indicates the state where I am. I am at state 0. This is where J is. If I have a match, I know I have to go to state J plus 1. And if I don't get a match, then I stay where I am. In the beginning, that is your trivial default, right? Please note the code is very confusing in the book. So we assume that the whole matrix is pre-filled with zeros. Okay? If you don't write Java, that is not necessarily the case. So if you write this in C, please pre-fill the matrix with zeros first. Okay? That is the first line in the code. We look at the pattern, the first character at position 0, and for the first alphabet character, then that must clearly be the same. Yes? Sorry. I match the first character in the pattern, yes, in row 0, yes, and I make it a 1. See? I match the first character in the pattern in the column 0, and I make it a 1. So If I got a B there, I would have been in column 0, so it would have been the second character who would have, second thing which would have been a 1. Yes. Okay, so I'm sort of jumping over my words. My pattern, I have 3 alphabet characters, A, B, and C. A is position row 0, row 1, row 2. Yes, we just write the A, B, C because it's easier to understand. So if the first character in the pattern is an A, I put a 1 there at position 0. If the first character in the pattern were a B, I would have initialized this to 0, 1, 0. Okay. So I just put in what is my first character in my pattern. Okay. And then off we go. What we always know X, no, we don't know that, sorry. X is my restart point. So X is where I want to backtrack to. So we're going to calculate X. Yes, my restart point. However, later on we'll see how X turns out. What I always know is that if I match the pattern here in position J, then the next state must be the next state, which is J plus 1. So this line represents the matching. This line calculates my restart point, the X. And over here, what I'm doing is I am copying the column that I have at my restart point. So I have a certain J, which is my restart point. I take the column at that point and copy it to my current position. Okay, so let's work through this. Because every now and then X updates, which is the difficult part. One down. In the beginning, I have nothing. Yes. So in the beginning, X is 0. Yes. J is 0. This was my initialization. What I now have to do is calculate X again. For the moment, we know that X will be 0, so cool. Yeah, X is 0, we'll get to it just now. What I want to do is I want to copy the column 1, 0, 0. Yes, that's that loop going through C for C equals. I copy this column to that column. Yes, so 1, 0, 0. But then I update for the match. Yes, I update for the match, and the match says if DFA pattern.char at JJ is J plus 1. So J is currently 1, so I have to make J is 0, so I have to update that to 1. No, why don't you stop me? J is currently 1, so I have to update that to 2. Yes? J is 0, J is 1. So I copy this column here, and I update that element to J plus 1. This represents that I am in the DFA, and I want to update where I am moving. If I have a match, I'm going to move from 1 to 2. Yeah. So can you see where I do that update? You have to get your indices straight. My update says DFA, the pattern at J. Now, what is the pattern at J is B. because I'm now in position 1. Yes? And therefore, I have to match that pattern with this thing. And if I have a B in position 1, I want to go to state 2. Okay? Yes? So I'm looking at the pattern. I see I have a match. Therefore, I must go to the next one. Okay? Right. So it's the copying of the column. And then let's look at, currently my X does not increase. X, my backtrack position, where I start testing the pattern again, is the same. Now, how do we calculate that backtrack position? We take the pattern at my current character, yes. So we look at that row, the current character that I have. In this case, it would have been a B. And I look at B of 0. Yes, because X is currently 0. So B of 0 was a 0, so X simply stays a 0. Yeah. 3 lines of code. What does the 3 lines do? After initialization, I take my restart column, I copy it to the current column. I amend the current column in the case where there was a match. Yes, that's the second line. This is just a copy of the restart column to the current column. I amend for a match, and then I check whether I should update my restart position. So that's the code sort of sorted out. So let's see where we get some interesting changes so that we can see what the difference would be. Right? And there we had an update for X. So let's see how this falls out. Here I am. We did this one. It worked. So what I would have to do, X is still 0. I copy my column at my restart position here. Yes. I update my match because I have an A, so that becomes J plus 1, which is a 3. And there we are, all happy. And now I have to update my X. X is still currently there, and here in the next step, X becomes 1. So X, this is my last update. Now I'm looking at X, right? And I claim that between this step and this step, X changed. And we can see, let's first look in the DFAY. If I have read ABA and I get another A, I would backtrack to 1. Okay? So my restart position is 1. So how does the code work? Let's see if I can actually manage this. I'll have to zoom out a bit. So can you still read it? Do you have your books open? Let's try. X equals the pattern where I am, DFA, the pattern where I currently am at J, of X. So the pattern where I currently am, in this example, where we see the change, the parent pattern where I currently am is A. So I have to go to DFA A in the I position. Yes, so I have to go of X. So I have to go there. It updates to 1. It represents that if I see a character I've seen before, it looks at that column and says, aha, I've read that character. What state must I go to? And in this case, ek is 10 uur klaar.
Kan ik even een project
Ja.
doen? Ja, die video neersteken.
Ja. No, not
Yes, yeah.
second year, second year.
Second year. Oh, okay. So,
They threw us out of 407 because of the construction.
you guys have class, I think. I'm just trying to convince more people to come to the game development talk.
Oh, yes, I wanted to tell you. Do you have a lecture at 10? What? Well, tell them, please. I thought it was.
Yeah. So depending on whether you want to come to applied maths or not, Rory is just here outside. I'm going to walk over with him now. And also maybe I talk to the honor students, and then perhaps you can convince Jaco to get his students off, so they would like to go.
I'll talk to Jaco.
Okay, cool.
So can you just explain to them what the lecture will be about? Quickly, 2 seconds.
Sorry.
It's just game development? What aspect of game development?
So it's game development. It's a little bit actually about my story and just the route that I've taken. It's development versus design, and it's a couple of real tours through just projects that our company has gone through. So things that I've been.
How much marketing and how much technical stuff?
I don't want to do any marketing, so.
Mostly technical?
It's
On the process of game development?
Yeah, it's functional versus product design. So it's a bit of everything, really, because I'm from a technical background, but I've moved more into a design holistic kind of thinking. So it's really a bit of everything.
These guys are hardcore programmers, so if you want the interest,
questions and make me look stupid, and I'll put you in contact with the people who can answer the questions.
There you go. Where is the talk?
It's Marinsky Building, Physics Building in room 3002.
3002. Okay, you've heard.
Thanks, guys. Thanks, John.
Good. Right. What can I say? Incidentally, you need a hell of a lot of applied maths to do graphics. So if you have a graphics game, then you need the applied maths. If you are just looking at game engines, any game engine is just a DFA. So it's a combination of computer science and applied maths. Next year, I'm having the first years again, not the second years. And what I do with the first years, to keep the balance between those who've programmed before and those who've never programmed, I have a lecture series on a Friday morning at 8 o'clock, go figure. But I get people in to give talks about things so that the people who can program can at least learn something more than just, this is an if, this is a while. So if you're interested in game development, graphics, and so on, I've had some very interesting talks in the past, and I plan to do it again next year, so not too late for you. Okay, back to Knut Morris. Brad, I have 5 minutes. How does the system know to increase X? How does it know where to backtrack to? Because it remembers the pattern in the position of X. Right? And so this process continues. You do your initialization, you use your current state to create your next state based on the pattern. This is a bit like self-reproducing code. I really like this algorithm. Has any of you written self-modifying code? Oh, go read up on it. It's easier in C than it is in Java. It's also fairly easy in assembler. So next semester, when you hit Willem Bester, who incidentally is not as sweet and gentle and forgiving and whatever as I am, so you better be on your toes. But ask him about self-modifying code. The idea about self-modifying code is if I have my Java there, I write a method that actually goes and changes it. Well, it doesn't work in Java. In C it does, because in C you have complete control over your program. But anyway, Java would stop you. I don't know. I don't think you can write self. Go and read up on self-modifying code. It is way cool. Do you have any idea how viruses work? My word, you do not know enough. You see, nou luister almal. There is a trick that you can pull. You know that in a normal Intel architecture, you have a data segment and a code segment. But if you go low level enough, you can force your data to execute. So you change your data and you make it execute, because in the end, it's just zeros and ones. And you can pull those kinds of tricks to embed a virus, for example, in a PDF document. Have you ever thought, if I get a virus, how does it come out of the bloody PDF document? Yes, you have to think wider than the little algorithms we do. Okay, right. So this is Knuth-Morris-Pratt. The idea is I initialize, I have a restart point based on my pattern. Yes, that is X. I copy my current restart column to my J column. I update my match point, yes, which means says I had a match in the pattern, I go to the next state. Then I have to calculate whether X has to be updated. Yes. And I simply look at whether my current position then is the match at the restart point. Are they the same? And then I update my X according to that. I think it's beautiful, beautiful code. And it's this long. Yeah? Okay, so that is what I expect you to know about Knuth-Morris-Pratt. Unfortunately, the proofs in the book are not doable, so no propositions. The next thing we do on Wednesday morning, and until further notice, I am trying to get the venue on Central Campus, probably in that silly mass. No, I didn't want the mass building. I don't like mass. No, I like the subject. I don't like the department. So, I love mass, the subject, not the department.